Okay, this is part 2 of lesson 3.6, and this is about the factor theorem. Basically, the factor theorem is very similar to the remainder theorem, except it's in a specific case. So an inquiry question is, using the remainder theorem, is there a way to determine a factor of a polynomial? And it says, think what it means to be a factor. Well, if you're truly a factor of a polynomial, let's look at a polynomial factored, actually, that might help. If we had, let's just pick a quadratic, x squared plus 5x plus 6. If we factor that, we're looking for two numbers that multiply to 6 and add to 5. The numbers that multiply to 6 and add to 5 are 2 and 3, so factored form would be x plus 2 times x plus 3. And if we were to do polynomial division or synthetic division of our polynomial by, say, x plus 2, we would end up with a quotient of x plus 3. And then what would the remainder be? Well, in our earlier division statement for the question we did in the remainder theorem, we did some polynomial division. We got a remainder of 2, and when we wrote our division statement, we've got a plus 2 there. If that plus 2 wasn't there, it would look like factored form. A number that is not there is basically the number 0. So if x plus 1 was a factor, we would end up with no remainder because that plus or minus part at the end wouldn't be there. There would be no remainder. And that's what the factor theorem is. Here's your remainder, 0. Okay. X minus a is a factor of f of x if the remainder is 0. And let's think about that for a second and see if that makes sense. That means, say we have our function, say f of x equals x squared plus 5x plus 6. We were told, according to the remainder theorem, that if we plugged in, say, -2 or -3 into our function, we should get a remainder. But we know that -2 and -3 are zeros for this quadratic. They're the x-intercepts. So if we plug in -2 or -3 into this function, we should be getting 0 for y, because they are x-intercepts. And that's essentially the remainder theorem. If you plug in a, or in this case -2 or -3 into our function, we should get a remainder of 0. If they're factors. So the factor theorem is just an extension of the remainder theorem. It's the specific case of when you get a remainder of 0. What's that mean? It means that whatever number you plugged into the original function was a factor, or was a 0 or was a root of the equation. And that x minus a would be a factor of that polynomial. So how can we use this to factor polynomials of degrees bigger than 2? Well, we have two polynomials here. We got an x cubed polynomial, we have another x cubed polynomial. We're going to use this factor theorem to factor polynomials with degrees bigger than 2. We learned last year that we can factor a quadratic by using a process called decomposition, or by looking for two numbers that multiply to the last number, add to the middle number, and we didn't need to use the factor theorem in polynomial division to factor. We could do it using one of those two strategies. But when the degree becomes higher than 2, it's much more difficult to do that, because we'd be looking for numbers that multiply to -6 and that add to, well, some combination of 4x squared plus x. That's a little confusing. If we know, though, in this case, that our factors, if the first term is x cubed, that factored form for this polynomial would have to start with x, because the first times the first times the first would need to be x cubed. And if there was a coefficient here like 2, we'd know one of those numbers in front of those x's would have to be 2. We also know something about the last number, -6. We know that the numbers at the end of each of these brackets need to multiply to -6. And that's where we start factoring polynomials with degrees bigger than 2. We look at that last number and we look for factors of -6. So what numbers multiply to -6? Well, -1 and 6, or 1 and -6, or -2 and 3, or 2 and -3. Those are our pairs of numbers that would multiply to -6. So if our factored form is going to look like this, the numbers on the end here have to be 3 of these numbers. Now we can use the remainder theorem to determine which of these are actually factors, and then we can factor it. We know that if we take our function and plug in a number that should go at the end of these brackets, or the correct a value, we should get a remainder of 0. So at this point, once we know what numbers we could try, we pick and choose and test. If it's 3 numbers being multiplied together to give us -6, we have to think about what those 3 numbers could be. Well, they could be -1, 6, and 1. They could be 6, 1, and -1. That's the same numbers. They could be -2, 3, and 1. They could be +2, -3, and 1. Or they could be 2, 3, and -1. It could be any combination of those. So let's pick one, plug it into the function, and see if it is a factor. And then we can work backwards from there. So let's try 1 first. The function at 1, and see what we get. If we get a value that's 0, we know that 1 is a correct a value, and then x minus 1 would be a factor. So let's try it. 1 cubed plus 4 times 1 squared plus 1 minus 6. 1 cubed is 1, 1 squared plus 4 is 4, plus 1 minus 6. 1 plus 4 is 5, plus 1 is 6, minus 6 is 0. F at 1 is 0. Therefore, x minus 1 is a factor. Once you've got one of the factors, then you can do some polynomial division to start chipping away at our degree 3 polynomial. So let's try some polynomial division. I'm going to use the synthetic style of division here. I'm going to take my a value 1, and I'm going to divide it into the coefficients of our polynomial. So 1, 4, 1, and -6. And following the rules of synthetic, we bring down 1, multiply, we get 1. We add down the column, 4 plus 1 is 5. Multiply 1 and 5, we get 5. Add down the column, we get 6. 1 times 6 is 6. Add down the column, we get 0 remainder. So what's that mean? Well, it means that f of x is our first factor, x minus 1, and then what we're left with. We've got 0 remainder, so that's our constant term, that's our x term, and that's our x squared term. So we have x squared plus 5x plus 6. And now we've taken that degree 3 polynomial and partially factored it. We've taken out an x minus 1, and we're left with a x squared plus 5x plus 6. And now, if we wanted to fully factor, we just have a simple quadratic left to factor. And we know how to factor a simple quadratic. We look for numbers that multiply to 6. It's actually the example we did right up at the top. X plus 2 and x plus 3 are our factors because 2 and 3 multiply to 6 and add to 5. X plus 2, x plus 3. That's what we call a happy coincidence. But now we have a fully factored polynomial. We went from a degree 3 expanded form, used factors of the last term, -6, through trial and error. We tested some of these values to see which ones would give us a remainder of 0. Once we found our first one, we did some polynomial division to partially factor and then end up with a single factor plus a leftover quotient, and then we factored the remaining quotient using factoring of quadratics, or factoring a simple quadratic. And now we have a fully factored polynomial. Why is this useful? Well, it's useful because if I asked you to graph this, you would know some information about the function, but not a ton. We'd know the y-intercept, we'd know the leading coefficient and the degree. So we'd know part of what we need to know to graph it. But if we factor it, now we know the full piece, or all the pieces, the full piece, all the pieces. We have x-intercepts, 1, -2, and -3. From the original equation, we have our y-intercept, and we have a leading coefficient and a degree. That's everything we need to know to graph. So in order to graph effectively, we need both forms of a polynomial. And using the factor theorem, polynomial division, and factoring of quadratics, we can get to factored form. So try applying that strategy to a second example. In this case, we want to factor x cubed minus 5x squared minus 2x plus 24. So start the exact same way. Look for factors of 24. There's a lot. By trial and error, start testing them. You don't have to write down every time you test it, but you do have to write down the one that works. So at a minimum, you have to write f at something equals 0. Therefore, f at something is a factor, or sorry, f minus something is a factor. So find one that works, gives you a remainder of 0. That's your first factor. Do some polynomial division, and then you'll be left with a binomial and a quadratic, and then factor your remaining quadratic to fully factor that. Try it. Check the solution on the course website, and we'll try some more factoring in class tomorrow. Thanks for watching.